What we did with this profile was we started noticing throughout this field of biomimicry, if you just look to nature, most of these complex problems have already been solved.
The humpback whale has tubercles that allow its fin to be more effective when it's taking sharp turns to corral krill.
We saw that and we thought, that's a similar thing that we're trying to do with wheels. So what can we do? How can we mimic the tubercle behavior and the features and put it on a rim to achieve the same sort of stability and efficiency?
The only difficult part that we had was to take a flipper that's supposed to work in straight flow to a wheel that is rotational while you're also getting straight flow over it.
What we were doing is really using the kind of profile of our hyperfoils to keep the air attached in certain regions.
A good way to explain what the hyperfoil does is to first imagine a vortex generator. You might have seen these things, they're pretty prevalent on commercial airline wings. If you look out the window, you see little tabs sticking up, and they're slightly askew from the wind direction. And what that does is it creates a pocket of low pressure to one side, which in turn makes a streamwise vortex of air that energizes the boundary layer, and that serves to keep the flow attached to the surface. Now, with the hyperfoil, it achieves the same thing, but it's one step more sophisticated. As the wheel pitches in yaw, the hyperfoil node becomes more prominent into the boundary layer and effectively creates more mixing and more energy transfer to keep the flow attached to the rim surface.
The undulating sawtooth RS shape with hyperfoil nodes stabilizes handling in gusting wind by increasing the frequency of wind vortex shedding. Lower frequency shedding produces larger, more powerful vortices, providing an unstable situation often referred to as buffeting. Higher frequency shedding produces a greater number of smaller, less powerful vortices, leading to greater wheel stability and rider control, saving watts typically expended trying to hold a line.
The dimples are hexagon-shaped instead of our traditional circular shape, and the harsh transition from one corner of the hexagon to the next makes for more effective mixing of that boundary layer.
And thus, creating a very stable, predictable platform.